Article 225 addresses outside branch circuits and feeders, and Article 230 covers services, while Article 240 focuses on overcurrent protection. This particular installation involves a 100 amps main service disconnect located on a pole at a commercial business. This disconnect supplies power to a shop building via a 3/0 overhead triplex feeder. Subsequently, a number 2 overhead triplex feeder is tapped off from the 3/0 triplex. This number 2 feeder then runs to a pole, transitions to a riser, and ultimately feeds a 100 amps main lug panel. This panel is dedicated to providing receptacles for truck block heaters, which are presumed to operate under a continuous load. Now, to dissect which code articles are most relevant, we need to consider the nature of each segment of the electrical system. The initial 100 amps main service disconnect and its immediate feed to the shop building could potentially fall under service requirements, but the tap creates a separate feeder. The crucial point here is that the number 2 overhead triplex feeder is tapped off from the 3/0 overhead triplex outside of the building. Because this tap occurs outside, the segment from the tap to the 100 amps panel is classified as an outside branch circuit or feeder, making Article 225 the most applicable code section. Article 230, concerning services, becomes less relevant because the 100 amps panel is not directly fed from the service entrance. It's fed from a tap off of a feeder. Article 240.21b5, which deals with tap rules for overcurrent protection, is also not directly applicable in this scenario. This is because 240.21b5 specifically addresses tap rules for branch circuits and not feeders. The number 2 triplex feeder is acting as a feeder to the 100 amps panel, not as a branch circuit. Therefore, our primary focus will be on Article 225 and general overcurrent protection requirements for feeders. A key consideration is whether a main breaker is required at the 100 amps panel. The general rule dictates that if a panel is fed by a feeder and contains more than 6 overcurrent devices, or if the feeder supplying the panel is rated over 100 amps, a main breaker is required. In this case, the question does not specify the number of overcurrent devices, but the context suggests that the panel serves multiple receptacles for truck block heaters, which implies there could be more than 6 branch circuits originating from this panel. Even without knowing the precise number of circuits, a main breaker is recommended and often required for safety and ease of maintenance. Furthermore, the absence of an equipment grounding conductor, or EGC, within the triplex feeder necessitates additional grounding and bonding measures at the 100 amps panel. Since the triplex feeder only consists of phase conductors and a neutral, it does not provide a dedicated path for fault current to return to the source. To ensure safety and proper operation of overcurrent protection devices, a supplemental EGC must be installed. This is typically achieved by driving a ground rod at the pole where the 100 amps panel is located and connecting it to the panel's grounding system. Additionally, all non-current carrying metal parts of the panel and the equipment it feeds, such as the receptacle boxes for the truck block heaters, must be properly bonded together into the grounding electrode system. In summary, the installation primarily falls under the purview of Article 225, governing outside branch circuits and feeders. A main breaker is generally required at the 100 amps panel, particularly if the panel serves multiple branch circuits. Finally, proper bonding and grounding, including the installation of a ground rod and supplemental EGC, are essential to ensure electrical safety because the triplex feeder does not include an equipment grounding conductor. Let's elaborate on each of these points to provide a more comprehensive understanding. Article 225 of the National Electrical Code addresses the requirements for electrical wiring and equipment located outside of buildings. It covers a broad range of installations including overhead and underground feeders and branch circuits, lighting, and other outdoor electrical equipment. When dealing with outside feeders, several key aspects need to be considered. Firstly, the ampacity of the conductors must be sufficient to carry the load they are intended to serve. This involves calculating the total load connected to the feeder, taking into account any demand factors or diversity that may be applicable. The conductors must be sized according to the ampacity tables in the NEC, ensuring that they can safely handle the continuous and non-continuous loads. Secondly, overcurrent protection must be provided for the feeder conductors. This is typically accomplished by installing a circuit breaker or fuses at the source of the feeder, sized to protect the conductors against overload and short-circuit conditions. The overcurrent protection device should be coordinated with the conductor ampacity to prevent nuisance tripping while still providing adequate protection. Thirdly, the feeder conductors must be properly supported and protected from physical damage. This may involve using conduit, cable trays, or other approved methods to protect the conductors from abrasion, impact, or exposure to the elements. The support should be spaced in accordance with the NEC requirements to prevent excessive sagging or strain on the conductors. Fourthly, the feeder conductors must be installed with adequate clearance from ground and other objects. The NEC specifies minimum clearance requirements for overhead conductors based on voltage and location. These clearances are intended to prevent accidental contact with the conductors by people or equipment. Fifthly, the feeder conductors must be properly grounded and bonded. This involves connecting the neutral conductor to a grounding electrode system such as a ground rod or metallic water pipe. The grounding system provides a low impedance path for fault current to return to the source, helping to clear faults quickly and prevent electrical shock hazards. In addition to these general requirements, Article 225 also includes specific provisions for certain types of outside installations, such as those involving agricultural buildings, marinas, and recreational vehicle parks. These provisions may address unique hazards or conditions that are present in these locations. Now let's consider the TAP rules as they relate to this installation, although it was already pointed out that Article 240.21b5 does not apply. TAPs are commonly used in electrical systems to supply power to smaller loads from a larger feeder. The NEC provides specific rules for tapping conductors to ensure that the tap conductors are properly protected and do not create a fire or shock hazard. The general rule for tapping conductors is that the tap conductors must have an ampacity that is at least 1/3 of the ampacity of the feeder conductors. This means that if the feeder conductors are rated for 100 amps, the tap conductors must be rated for at least 33.3 amps. However, there are some exceptions to this rule. One exception is that the tap conductors can be shorter than 10 feet if they are enclosed in conduit or otherwise protected from physical damage. Another exception is that the tap conductors can be longer than 25 feet if they are protected by an overcurrent device at the point where they connect to the feeder conductors. In this case, the number 2 overhead triplex feeder is tapped off from the 3/0 overhead triplex. The ampacity of the number 2 conductors must be sufficient to carry the load connected to the 100 amps panel. The overcurrent protection device at the source of the number 2 feeder must be sized to protect the conductors against overload and short-circuit conditions. Finally, let's discuss the grounding and bonding requirements for the 100 amps panel. Grounding is the process of connecting the electrical system to the earth. Bonding is the process of connecting all of the non-current carrying metal parts of the electrical system together. Grounding and bonding are essential for electrical safety because they provide a low impedance path for fault current to return to the source. This helps to clear faults quickly and prevent electrical shock hazards. The NEC requires that all electrical equipment be properly grounded and bonded. The specific grounding and bonding requirements vary depending on the type of equipment and the location of the equipment. In general, the grounding electrode system must consist of one or more of the following grounding electrodes: a metal underground water pipe, a ground rod, a ground ring, or a concrete encased electrode. The grounding electrode must be connected to the neutral conductor at the service entrance. The non-current carrying metal parts of the electrical system must be bonded together using bonding jumpers. Bonding jumpers must be sized according to the NEC requirement. In the case of the 100 amps panel, the grounding electrode system must be connected to the neutral conductor at the panel. The non-current carrying metal parts of the panel, such as the enclosure and the equipment grounding conductors, must be bonded together using bonding jumpers. Additionally, because the triplex feeder does not include an equipment grounding conductor, a supplemental EGC must be installed. This can be accomplished by driving a ground rod at the pole where the panel is located and connecting it to the panel's grounding system. This installation is subject to the requirements outlined in the National Electrical Code, or NEC. Understanding and adhering to these requirements is critical for ensuring the safety and compliance of electrical installations. Here's a further breakdown of key areas to consider. Firstly, Article 225 outside branch circuits and feeders. This article covers the requirements for outside electrical wiring on buildings, structures, or poles. It includes information on wiring methods, conductor support, clearances, and overcurrent protection. The primary goal is to ensure that electrical installations outside buildings are safe and reliable, protecting against environmental factors and physical damage. Secondly, conductor ampacity and sizing. Correct conductor sizing is crucial. The ampacity of the conductors must be sufficient to carry the intended load, considering any applicable demand factors. NEC Table 310.15b16 provides guidance on ampacity based on conductor type and insulation. Overcurrent protection should be coordinated with the conductor ampacity to prevent overloads and short circuits. Thirdly, overcurrent protection. Overcurrent protection devices, such as circuit breakers or fuses, are essential for protecting conductors and equipment from excessive current. The overcurrent protection device should be sized appropriately for the conductor ampacity and the load it serves. NEC Article 240 provides detailed requirements for overcurrent protection. Fourthly, grounding and bonding. Grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to return to the source, helping to trip overcurrent protection devices and prevent electrical shock hazards. Bonding ensures that all non-current carrying metal parts are electrically connected, minimizing voltage differences and providing a low impedance path for fault current. Fifthly, grounding electrode system. A grounding electrode system is required to connect the electrical system to the earth. Common grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes. The grounding electrode system must meet the requirements of NEC Article 250. Sixthly, equipment grounding conductor EGC. An equipment grounding conductor provides a path for fault current to return to the source from non-current carrying metal parts of equipment. The EGC must be sized according to NEC Table 250.122 and must be installed in accordance with NEC Article 250. Seventhly, bonding jumpers. Bonding jumpers are used to connect non-current carrying metal parts together, ensuring electrical continuity and providing a low impedance path for fault current. Bonding jumpers must be sized according to NEC Table 250.102 and must be installed in accordance with NEC Article 250. Eighthly, tap rules. Tap rules allow conductors to be tapped from a larger feeder to supply smaller loads. The tap conductors must meet certain requirements to ensure that they are properly protected and do not create a fire hazard. NEC Article 240.21 provides detailed requirements for tap conductors. Ninthly, main breaker requirements. A main breaker is often required in a panel to provide a means of disconnecting all power to the panel. The main breaker must be sized appropriately for the load served by the panel. NEC Article 408 provides requirements for panel boards, including main breaker requirements. Tenthly, continuous load. A continuous load is a load that operates for 3 hours or more at a time. Continuous loads must be calculated at 125% of their rated current when determining conductor ampacity and overcurrent protection. NEC Article 210.20 provides requirements for continuous loads. Let's delve into the specifics of grounding and bonding in this scenario. The absence of an equipment grounding conductor EGC in the triplex feeder line necessitates a local grounding electrode system at the 100 amps panel. This is because a dedicated fault current path is required to ensure that overcurrent protection devices function correctly and quickly in the event of a ground fault. Here's a detailed look at the necessary steps. Firstly, ground rod installation. Drive a ground rod into the earth near the 100 amps panel. The ground rod should be at least 8 feet long and should be driven into the earth until at least 8 feet of its length is in contact with the soil. The top of the ground rod should be flush with or below the surface of the earth. Secondly, ground rod material. The ground rod should be made of a material that is suitable for direct burial in the earth, such as copper-clad steel or stainless steel. The ground rod should be at least 5/8 inch in diameter. Thirdly, connecting to the ground rod. Use a listed grounding clamp to connect a grounding electrode conductor GC to the ground rod. The grounding clamp should be made of a material that is compatible with both the ground rod and the GC. Fourthly, grounding electrode conductor GC sizing. The GC must be sized according to NEC Table 250.66. The size of the GC depends on the size of the ungrounded service conductors or the equivalent size for a service entrance cable. Fifthly, running the GC to the panel. Run the GC from the grounding clamp on the ground rod to the grounding busbar in the 100 amps panel. The GC should be run in a straight line and should be protected from physical damage. Sixthly, connecting to the grounding busbar. Connect the GC to the grounding busbar in the 100 amps panel. The grounding busbar is typically a copper bar that is mounted inside the panel and is used to terminate all of the grounding conductors in the panel. Seventhly, bonding the panel. Bond the metal enclosure of the 100 amps panel to the grounding busbar. This can be done by using a bonding jumper. The bonding jumper should be sized according to NEC Table 250.102. Eighthly, bonding other metal parts. Bond any other non-current carrying metal parts that are likely to become energized to the grounding busbar. This includes metal conduit, metal enclosures, and metal equipment. Ninthly, testing the grounding system. Test the grounding system to ensure that it is properly installed and is providing a low impedance path for fault current. This can be done by using a ground resistance tester. Tenthly, documentation. Document the installation of the grounding system. This includes recording the location of the ground rod, the size of the GEC, and the results of the grounding system test. By following these steps, you can ensure that the 100 amps panel is properly grounded and bonded, providing a safe and reliable electrical system. Remember that local codes and regulations may have additional requirements, so it's always a good idea to consult with a qualified electrician or electrical inspector before starting any electrical work. It is important to properly bond all metallic components of the electrical system together to create a low impedance path for fault current. This includes the metal enclosure of the 100 amps panel, any metal conduit or raceways, and any metal equipment connected to the panel. Bonding helps to ensure that all metallic parts are at the same electrical potential, minimizing the risk of electric shock. Here's how to ensure proper bonding. Firstly, bonding jumpers. Use bonding jumpers to connect all non-current carrying metal parts of the electrical system together. Bonding jumpers should be sized according to NEC Table 250.102. Secondly, bonding to the grounding busbar. Connect all bonding jumpers to the grounding busbar in the 100 amps panel. The grounding busbar is typically a copper bar that is mounted inside the panel and is used to terminate all of the grounding conductors in the panel. Thirdly, bonding lock nuts and bushings. Use bonding lock nuts and bushings when connecting metal conduit or raceways to the 100 amps panel. Bonding lock nuts and bushings provide a secure electrical connection between the conduit and the panel enclosure. Fourthly, direct burial. Ensure that all metal parts that are buried in the earth are properly bonded together. This includes metal water pipes, metal gas pipes, and metal underground storage tanks. Fifthly, aluminum conductors. When using aluminum conductors, use listed connectors and fittings that are specifically designed for use with aluminum. Aluminum connectors and fittings are designed to prevent corrosion and ensure a reliable electrical connection. Sixthly, stainless steel. When using stainless steel components, use listed connectors and fittings that are specifically designed for use with stainless steel. Stainless steel connectors and fittings are designed to prevent corrosion and ensure a reliable electrical connection. Seventhly, inspection. Inspect all bonding connections to ensure that they are tight and secure. Loose or corroded bonding connections can create a high impedance path for fault current, which can increase the risk of electric shock. Eighthly, local codes. Follow all applicable local codes and regulations when installing bonding connections. Local codes may have additional requirements for bonding. Ninthly, qualified electrician. If you are not comfortable installing bonding connections yourself, hire a qualified electrician to do the work. A qualified electrician has the knowledge and experience to install bonding connections safely and correctly. Tenthly, testing. Test the bonding system to ensure that it is properly installed and is providing a low impedance path for fault current. This can be done by using a low resistance ohmmeter. This comprehensive grounding and bonding approach ensures that the electrical system is safe and compliant with the NEC, reducing the risk of electrical shock and fire hazards. Now let's address the necessity of a main breaker at the 100 amps panel in more detail. According to the NEC, a main breaker is typically required in a panel board if the panel board is supplied by a feeder and contains more than 6 overcurrent devices, or if the feeder supplying the panel board is rated over 100 amps. In this case, the 100 amps panel is fed by a number 2 triplex feeder, and the panel is used to supply power to multiple truck block heaters. Given that truck block heaters are often individually circuited, it is highly likely that the panel contains more than 6 overcurrent devices. Therefore, a main breaker is required. Here are some detailed points to consider. Firstly, number of overcurrent devices. Count the number of overcurrent devices in the 100 amps panel. If there are more than 6 overcurrent devices, a main breaker is required. Secondly, feeder rating. The feeder supplying the panel is rated at 100 amps. If the feeder were rated over 100 amps, a main breaker would be required regardless of the number of overcurrent devices in the panel. Thirdly, disconnecting means. A main breaker provides a convenient means of disconnecting all power to the panel in the event of an emergency or for maintenance purposes. This is an important safety feature. Fourthly, NEC requirements. NEC Article 408.36 provides requirements for overcurrent protection in panel boards. This section specifies when a main breaker is required. Fifthly, local codes. Check with local codes and regulations to see if there are any additional requirements for main breakers in panel boards. Some local codes may require a main breaker regardless of the number of overcurrent devices or the feeder rating. Sixthly, breaker size. The main breaker should be sized appropriately for the load served by the panel. The main breaker should not be larger than the ampacity of the feeder conductors. Seventhly, installation. The main breaker should be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. Eighthly, inspection. Have the installation of the main breaker inspected by a qualified electrical inspector. Ninthly, safety. Always de-energize the panel before working on any electrical components. Use appropriate safety equipment, such as rubber gloves and safety glasses. Tenthly, qualified electrician. If you are not comfortable installing a main breaker yourself, hire a qualified electrician to do the work. A qualified electrician has the knowledge and experience to install a main breaker safely and correctly. By having a main breaker, the safety and functionality of the electrical system are significantly enhanced. Now let's focus on continuous loads, which are critical for accurate electrical calculations and safety compliance. A continuous load is defined as a load that operates for 3 hours or more at a time. According to the NEC, continuous loads must be calculated at 125% of their rated current when determining conductor ampacity and overcurrent protection. This is to account for the heat buildup that occurs when a load operates continuously. Here are some key considerations for continuous loads. Firstly, definition. A continuous load is a load that operates for 3 hours or more at a time. This is an important definition to understand because it affects how the load is calculated. Secondly, calculation. When calculating the load for a continuous load, multiply the rated current of the load by 125%. This will give you the adjusted current that should be used for determining conductor ampacity and overcurrent protection. Thirdly, conductor ampacity. The conductors that supply a continuous load must have an ampacity that is at least 125% of the rated current of the load. This is to ensure that the conductors can handle the heat buildup that occurs when the load operates continuously. Fourthly, overcurrent protection. The overcurrent protection device that protects a continuous load must be rated at not less than 125% of the rated current of the load. This is to ensure that the overcurrent protection device does not trip unnecessarily due to the heat buildup that occurs when the load operates continuously. Fifthly, NEC requirements. NEC Article 210.20 provides requirements for continuous loads. This section specifies how to calculate the load for a continuous load and how to size the conductors and overcurrent protection. Sixthly, truck block heaters. Truck block heaters are typically considered continuous loads because they often operate for extended periods of time, especially in cold climates. Seventhly, load management. Consider using load management techniques to reduce the load on the electrical system. This can include using timers to turn off loads when they are not needed or using energy-efficient equipment. Eighthly, local codes. Check with local codes and regulations to see if there are any additional requirements for continuous loads. Some local codes may have more stringent requirements than the NEC. Ninthly, qualified electrician. If you are not comfortable calculating the load for a continuous load or sizing the conductors and overcurrent protection, hire a qualified electrician to do the work. A qualified electrician has the knowledge and experience to perform these tasks safely and correctly. Tenthly, safety. Always to energize the circuit before working on any electrical components. Use appropriate safety equipment, such as rubber gloves and safety glasses. When truck block heaters are involved, which is the case in this scenario, it's safe to assume they operate continuously, necessitating the 125% calculation factor. By considering the continuous load requirements, the electrical system's safety and reliability are greatly enhanced, reducing the risk of overheating and potential fire hazards.